In 4.7, we're going to be looking at a technique that we can use when we evaluate limits of the indeterminate form 0 over 0 or infinity over infinity. And that rule is what we call L'Hopital's rule. So what L'Hopital's rule says is that if you get a 0 over a 0, or if you get infinity over infinity, then when you evaluate the limit, what you could do is just take the derivative on the top and the derivative on the bottom separately, and then reevaluate the limit. So again, take the derivative on the top, the derivative on the bottom, separately, and reevaluate the limit. The key thing to remember is you have to have the 0 over 0 or infinity over infinity form before you can use L'Hopital's rule. So in example 1a, we were introduced to the limit as x goes to 0 of sine of x over x in a previous section. And remember that that limit was equal to 1. It was just something that you were given. But we didn't really prove it. What happens when we do put in 0 for x is the sine of x becomes 0 and the denominator x is 0. So this is actually an indeterminate form. But since it's 0 over 0, that gives me the justification of using L'Hopital's rule, which says that this limit as x goes to 0 is going to be equal to the derivative of the top, so the derivative of sine of x is cosine, over the derivative of the bottom, the derivative of x is 1. And now what I can do is I can reevaluate this limit. Plugging in 0, cosine of 0 is just 1, so it becomes 1 over 1. This is a very powerful tool, something to remember, and it's very important. Did you actually get a 0 over 0 or infinity over infinity before using L'Hopital's rule? That's the only time you can use L'Hopital's rule. Let's look at another example. In example B, if I were to plug in 1 for x, I get 0 over 0, which again is an indeterminate form. So I'm going to use L'Hopital's rule to say that this is equal to the limit as x goes to 1, the derivative on the top is 1. The derivative on the bottom is going to be, so the square root of x derivative would be 1 over 2 times the square root of x. And the minus 1 is just 0, so I'm not going to worry about that. So now let me evaluate this limit. As x goes to 1, I get 1 over 1/2, which is going to be equal to 2. So it's a very, very powerful technique to evaluate limits with the indeterminate form 0 over 0 or infinity over infinity. We'll go through a few more examples. Let's look at C. We have the limit as x goes to pi over 2 from the left of secant over tangent plus 1. So if I were to plug in pi over 2, secant is going to be undefined. And there's actually an asymptote at pi over 2. So if we approach from the left, secant, the graph of secant goes to positive infinity. Tangent of pi over 2 is also undefined because there's a vertical asymptote. As we approach from the left, tangent goes to positive infinity. If I add 1 to that, that's not going to make a difference. So I have infinity over infinity, and that justifies me using L'Hopital's rule to take the derivative of the top and the bottom separately. So our limit as x goes to pi over 2 from the left will be the derivative of secant is going to be secant tangent And the derivative of tangent is secant squared. And then the plus 1 is just plus 0. Okay, let's reevaluate. But before I do that, I notice that I have secant on the top and bottom. So I'm going to go ahead and reduce to write this in a simpler form by canceling a secant on the top and bottom. I have tangent over secant. When I reevaluate, unfortunately, I still get infinity over infinity. So what I could do is I could try using L'Hopital's again. The problem is I'm going to get back to where I started at the second step. It's just going to be flipped. So for example, if I were to take L'Hopital's again, this would be the limit as x goes to pi over 2 from the left of secant squared x over secant x tangent x. So you notice that this is similar to that second step, it's just flipped. And I'll still get infinity over infinity. So instead what I'm going to do is notice that tangent over secant can probably be simplified further if I write everything in terms of sine and cosine. Again, I don't want to use L'Hopital's again because this will just keep repeating. I'll have tangent over secant, secant over tangent, tangent over secant, secant over tangent. And I'll always get infinity over infinity. So tangent is sine over cosine, and secant is 1 over cosine. So hopefully you'll notice that the cosine cancels, and this just becomes the limit as x approaches pi over 2 from the left of sine of x. And then plugging in pi over 2 to sine of x, I get that that's equal to 1. So you can use L'Hopital's rule more than once. But again, remember, you always have to have infinity over infinity. And remember, it can also be negative infinity over infinity, or 0 over 0. Let's look at another example. If I evaluate this limit and plug in infinity for x, I get infinity minus 1 on the top, which is just infinity. On the bottom, I'll have infinity plus infinity, which is still infinity. And I have an indeterminate form of infinity over infinity. So if I use L'Hopital's and take the derivative on the top and the bottom separately, I'll get 16 x to the third on the top. On the bottom, I'll get 9x squared plus 10. Oops, 10x. I lied. Now, if I reevaluate, the problem is I'm still getting infinity over infinity. However, that just means I can use L'Hopital's again. So the derivative on the top is going to be 48x squared. And on the bottom, I'll get 18x. And again, oops, plus 10. I keep forgetting that part. Again, I still get infinity over infinity, which is fine. That tells me I can use L'Hopital's. Take the limit as x goes to infinity of 96x over 18. Finally, I don't have x in the denominator. So now when I plug in infinity, I just get infinity over 18, which is just infinity. That is not an indeterminate form. That's the limit. So let's look at a few more cases. And then that's it for this section. It's a pretty short section. So let's look at these two indeterminate forms. 0 times infinity and infinity minus infinity. I don't know what those mean. And I can't use L'Hopital if I get that indeterminate form, because you can only use L'Hopital when you have the fraction 0 over 0 or infinity over infinity. So let's see what happens. In example 2a, if I plug in infinity for x, this limit is going to be equal to infinity squared, which is infinity, times, if I plug in infinity for the x squared, I get 1 over infinity, which is 0, and sine of 0 is 0. So that's an indeterminate form, and I cannot use L'Hopital's. However, I can create a fraction and then see if I can use L'Hopital's. So I'm going to keep the sign of 1 over x squared where it is. And I'm going to move the x squared into the denominator by writing it as 1 over x squared. So notice that these two expressions are equal. But now what I've done is I've created a fraction where if I put in infinity, I now get sine of 0, which is 0, over 1 over infinity is 0. So I've created a fraction where I can use L'Hopital's because I do now have 0 over 0. I'm going to take the derivative on the top. And don't forget that the derivative on the top involves a chain rule, because this is not just sine of x. This is sine of 1 over x squared. So by the chain rule, derivative of sine is cosine. The inside stays the same, and then I'm going to multiply by the derivative of the argument or the inside function. Now what I notice is that the argument on cosine is the exact same as my denominator. It's 1 over x squared. So when I take the derivative with respect to x of 1 over x squared, I'm actually not going to take the derivative. Because since these guys are the same, notice that the derivative of 1 over x squared, derivative of 1 over x squared, is going to cancel. However, you can compute the whole thing and then simplify it. But sometimes these little gems come in that make computations a lot easier. So what happens is we just have cosine of the argument is 1 over x squared. Putting in infinity, this is just equal to the cosine of 0, which is 1. Now let's look at our last example. So we're just doing a bunch of different types of problems that could come up with indeterminate forms. Okay, we're going to look at the limit as x goes to 0 from the right of cotangent minus 1 over x. So cotangent has an asymptote at 0. If you approach 0 from the right, cotangent is going up to positive infinity minus 1 over 0. Remember, that's either going to be positive or negative infinity. But since we're approaching 0 from the right, that's going to be positive infinity. And we have the indeterminate form, infinity minus infinity. So I need to create a fraction and then see if I can use L'Hopital's. The only thing I could see to do is to change cotangent to cosine over sine. So if I write this as cosine of x over sine of x, I've created a fraction. The problem is I cannot use L'Hopital's because this is not one fraction. I have a subtraction of 2 fractions. But that can be fixed by combining these two with the common denominator x times sine of x. So this will become x cosine of x minus sine of x in the numerator over x sine of x. So I've created this fraction. And now let's see if I can use L'Hopital's. So if I put in 0, this becomes 0 minus 0 on the top, which is 0, and then 0 in the denominator. So now I can use L'Hopital's to take the derivative of the top and the bottom separately and then reevaluate my limit. You have to be careful though, because when we take this limit, we have to use the product rule on x times cosine of x, since it's a product of two functions. So the derivative of x is 1. I'm going to keep cosine, plus keep the x, derivative of cosine is negative sine, minus the derivative of sine is cosine, all over x. Sine of x is product rule again. So I'm going to do derivative, keep the sine of x, plus keep the x, derivative of sine is cosine. So cosine minus cosine is gone. I'm going to clean this up a little bit. On the top, I'm going to have negative x sine x. So what I'm going to do is I'm going to pull the negative out. So I don't want to deal with that. And write this as x sine x in the numerator, and then sine of x plus x cosine of x in the denominator. So let's go ahead and reevaluate. If I put in 0, I get 0 in the numerator, and I get 0 plus 0, so 0 in the denominator. So indeterminate form, but I could use L'Hopital's again. Now I'm going to try to use L'Hopital's again since I don't see algebraically anything that will simplify. So I still have this negative on the outside. The limit as x goes to 0. From the right, product rule on the top will be sine x plus x cosine of x. The derivative of sine is cosine, plus use the product rule on x cosine of x to get cosine of x plus x times negative sine of x. Now I could reevaluate the limit as it stands, but I think I am going to rewrite this as sine of x plus x cosine of x over cosine plus cosine is 2 cosine of x minus x sine of x. Okay, so let's see if this helps. Now if I put in 0, I'm going to have 0 plus 0 in the numerator, and I still have this negative on the outside. In the denominator, though, cosine of 0 is 1. So this becomes 2 minus 0. Okay? In other words, 0. This is not an indeterminate form. This is not a form where I use L'Hopital's. This is the limit. It's just 0. Okay, so we've done a bunch of examples on how you could use L'Hopital's to evaluate limits of indeterminate forms, and that's it for this section.